Hello everyone. So today we'll be presenting a topic on artificial intelligence. My team members are Monica and Shumaila. So let's go ahead and see what we have for today. Some of the papers that we'll be discussing today are comparative analysis of search algorithms and severe weather avoidance using informed heuristic search. So these are the two papers that we'll be discussing today. So I'll be taking up the first paper. And let's go ahead and stop it. Okay. So as we all know, artificial intelligence mainly aims at uh, getting computers to think like humans and behave like humans. So that is what is the main aim for artificial intelligence. So artificial intelligence has two subsets in it, which is machine learning and deep learning, as you can see in the image here. And uh, data science is also a field uh, which is intertwined with artificial intelligence, machine learning, and deep learning. So we'll be learning about some of the searches, that is uniformed and informed searches today. So here you go. So uniform search is something that is simple and it follows a blind search method, such as brute force, because it doesn't have to have a logic to reach to its target. So what it does is it goes through, it tries to find the best solution possible at that particular time without any idea as to whether it's optimal or not. So some of the searches that are an ununiform search are breadth first search, depth first search, uniform cost search, iterative deepening, and bidirectional search. And when we check out informed search, it's type of a heuristic search where we have a function which will provide us it will let us know a particular path that needs to be taken to reach the or a function or an algorithm that lets us tell how to take the path to reach the end goal or the goal state. So some of the examples are hill climbing, steep hill climbing, A star, AO, and best first search. Next, we'll be going through the breadth first search, that is BFS. So here in this particular search algorithm, we'll go by levels. So first we search for one level, and then once that whole level is traversed, we go to the next level. And this is implemented using a queue. So as we know, queue is first in, first out. And some of the formulas that we use for calculating time complexity and space complexity are here, where B is the branching factor and D is the solution depth. So as we can just go through this example in brief. As we can see, at node 0 or the level 0, we have node 1, and node 1 has three branches, that is node 2, node 3, and node 4. So these three are in the next list that we'll have to search. As we go ahead from node 2, we'll find that we have 6 as the only child node, and we'll add that to the queue. And then the next in the queue is the queue node 3. So like this will traverse through each layers or each levels in the graph to reach the goal state 8. So the table here has the details as to how each step is taken. So next we have some of the advantages and pros and cons of these breadth first search. So in breadth first search, it can be used when the graph or the solution has very less nodes or fewer curves. So the shorter, and it can also be used in situations where there is only one shortest path and it can be reached in one go, and it doesn't have to have and the graph or doesn't have to require a lot memory, like its memory is not an issue. So in these cases we can use breadth first search. And in where we can't use breadth first search is when the solution is long, or when the graph is very long and it takes a lot of time to reach the uh, end goal or the goal state, or when we have a defined path, or like I said, heuristic function, which if it's available, then we can't use BFS. That's a breadth first search. And when memory required is very high, we'll have to like avoid using BFS. And some of the applications where we can use them is in finding the shortest span in an unweighted graph, or when we have or it can be used in shared networks, social networking websites to find the nearby nodes, and even in the GPS navigation systems. And also it can be used to determine a graph, whether a graph is a bipartite or not. So the next topic is depth first search. So this is the next algorithm. So in this algorithm, we'll go from will not go in a layer format. We'll do the search in a depth, like where we expand the nodes based on their depth. So once each node's depth is reached, then we come back and start from the next branch. So this algorithm uses the stack, is implemented using a stack. So we'll be using the principle last in first out. As you can see, this is the formulas that we have for calculating time complexity and space complexity. B is same, the branching factor, whereas M is the maximum depth. Similarly, we have used the same diagram which we use for BFS. So here the how to get to the goal state is a bit different, because first from the level 0 we first traverse to the branching nodes, that is 4, 3 and 2. Those nodes are put in the open list in the stack, and then from we'll first traverse, or we'll first expand the node 2. From node 2 we'll go to node 6, and node 6 doesn't have a child node, so we'll come back to node 3, and from node 3 we'll go into node 5, and node 5's child, that is 6, is already node 6 has already been traversed or searched, so we'll add node 7, and then from node 7 we'll be able to reach the node 8. So that is the how we are using the depth first search to search in a graph to reach the goal state. Then we have some of the applications, where is it applicable and what are its applications. So we know if we know the sequence in which the graph has to be explored, then we can do using depth first search, we can use that particular sequence to achieve our goal in the first search itself. So that is useful. So this DFS is useful in that particular scenario. And if the graph contains a lot of loops or never ending cycle, like, or if the graph is like never ending, very lengthy, in that case also it's applicable. Or when the amount of memory that is needed is limited, this particular DFS is applicable. And some of the applications where we use it is where this DFS is applicable is to find loops in a graph, or to find components that are strongly connected. Like how do I say, in a graph each and every node has to be it should be connected in such a way that you can traverse through all other nodes from that particular node. So if this DFS is used to search that particular condition as well, and it is mostly used to used in puzzles that can have only one solution. Like it is used to solve puzzles that have only one solution. Next search is uniform cost search. So uniform cost search is used to find the cheapest path that can be taken. So it uses priority queues to be implemented. And how the cost is calculated for each node is done with this formula. C of M is equal to C of N plus C of N comma N, where C of M is the cost of current node, C of N is the cost of the previous node, and C of N comma M is the weight of the edge. Time complexity and space complexity is calculated using these formulas, where C is the optimal solution cost and E is the cost that is taken for each step to get close to the goal node. So as you can see, we start with the node 1 of 1, and in the table here, the details in the brackets are the cost for that particular node. So as you can see, from node 1 we can traverse to node 2 and node 5. So node 2, the cost will be 2, and for node 5 it will be 1. So from then, when we have to look for the node that has the least cost, that is node 5. Then from node 5 we'll be able to traverse to node 9, and node 9's cost will be a sum of the weight on the edges, that is 1 plus 1, 2. So 1 to 5 is 1, and 5 to 9 is 1, so 2. So that way we'll be traversing the whole graph until we reach the goal state 12. In middle, you can see that some of the states here are cancelled. That is because from a different node, if we reach to the same node 10 in this case, we'll have to remove the node that has a larger or higher cost from the queue. So that is what happens when we are in this particular so that is one of the advantage in this particular graph, where we can remove the node that has higher cost, it like the predecessor or before this, if the same node was added to the queue. So this is how we perform the uniform search, cost search. And then we have some of the applications where this can be applicable. So uniform cost search is applicable when the space requirement is less, and when the search is simple, or when the only the shortest, or when the shortest path is not required. And then the applications, like it can be used in to find solutions to maze related problems, and also it is used in pathfinding problems. Next we have the A star search. So A star search, it mostly focuses on finding the optimal solution, and it is a combination of uniform cost search and the heuristic search. So it uses some of the heuristic functions that it uses are Euclidean distance, Manhattan distance, and diagonal distance. The cost formula is a bit different when compared to uniform cost search. As you can see, we have different functions where f of m is the most reduced aggregated cost, and h of m is the heuristic function. And time complexity and space complexity is defined, is mentioned here. So as we can see, the open list, when we search in this, how to search for the end goal. So here, when we go through this, so whatever weight for node 1, as you can see, it has a 12 on its, that is a solution, sorry, that is the solution depth, that is 12. So as you can see, that is the on 1 we have 12. So that is what we have updated in the open list and the closed list table. Now once as we start traversing, we have node 2 and node 5. Node 2's depth can be like whatever is on top of the node, that is 10, plus the root, like what is the weight on the edge, that is 2. So we'll have 2, and the weight cost will be 12. Similarly, for node 5, we have 13, which is 12 plus 1 from node 1. So this way, and we'll also have to put in the make sure that the list, open list, has the least cost in the node at the beginning. So now we have 2 and 5. From this, we have 2 as the least cost node. So then from 2, we can traverse to node 6 and node 3. Node 3's total cost would be 16 plus 3, that is 19. And for node 6, it will be 7 plus 5, that is 12. So as now in the queue, we have 6, which has the least cost. So we'll take that route, like we'll take this node 6, and then from node 6, when we see we have node 5, but to reach node 5, the cost from node 6 is higher, so we'll leave the previous cost there. And for we can reach to node 7 and node 10. At node 7, the cost will be 11 plus 6, that is 17. And for node 10, it will be 4 plus 9. that is 13. So as you can see now, the least cost is for 5 and 10. So we'll first go ahead and traverse from 5, and from 5 we can reach only to node 9 now. So node 9 is added to the queue, and then as we can see, node 10 is the only node that has least cost. So then we'll go from node 10, and from node 10 we can only reach to node 11, and from node 11 we can reach to node 12. So that is how we reach the goal state. So the next slide we have is for the applications where we can use A star. So it is used in traffic navigation systems, and it is used in some games, and it is also used to find shortest path on a graph, and it is also used to avoid water obstacles by finding the path for high-speed unmanned vehicles. Next, we have the best first search. So best first search is a combination of breadth first search and depth first search, and it is implemented using a priority queue. It is also called as the greedy search because it utilizes the functionalities of both depth first search and breadth first search. And the time complexity and space complexity is mentioned here. And we have some of the applications where it can be used is in games and in web crawlers. Next, we have the slide where we have the comparison for each search algorithms. So the comparison is done based on 4 different parameters, that is time complexity, space complexity, optimality, and completeness. So in the time complexity, what is time complexity? It is the amount of time taken for an algorithm to solve an the amount of time taken to solve an algorithm is called time complexity, whereas space complexity is the amount of memory it is required by an algorithm to search. And then optimality is the algorithm solution. So we are checking whether the given algorithm solution is optimal or not. So that's why it's yes or no here. And then the completeness. So completeness is where we can say that for a given problem, will this algorithm will be able to give us a at least one single calculation, or will there be a solution with the given calculation for this algorithm? So even that is indicated in Boolean indicators, that is yes or no. So as you can see, all these algorithms. So BFS, we can reach to a solution. And for DFS, if the loop is infinite, we can't. So we have whether we have it as no. And same thing with best first search, because it again uses DFS in it. So we can't say it's optimal, but we can reach to completion because it uses the BFS function. And then now we have the conclusion slides for this paper. So conclusion can be, we can draw this conclusion using the closed list and the open list for uniform cost search and A star algorithm. So as you can see in the uniform cost search, we use 11 different nodes to reach the goal state, whereas in A star, we had only 6 nodes and we could reach the solution goal state earlier. And also UCS, it consumes more time to get to the solution. So using this uh, these two differences, we can say that A star algorithm is more efficient and optimal when compared to UCS. And also when cost is similar in different algorithms, we choose that BFS, breadth first search, instead of uniform cost search, as it searches the shallowest unexpected nodes. So this way, using these all factors, we can summarize that heuristic search is more efficient in comparison to blind search. So now I'm done with my topic. So Shumaila will take over from now.
Hello everyone, this is Shumaila Sefi, and now I will present the weather avoidance using informed search algorithm. So here we will discuss about some technologies in by which we can avoid the severe weather conditions, especially for the aircrafts. So we will discuss. Next slide, please, Wanda. So we can find the weather condition through the Gaussian function. There is a uh, there is a function which is mainly used to detect the intensity of thunderstorm in bad weather. So the function, we can get a more realistic image with that function, because it is a 2D function, and we can find the weather condition at any point in like XY function. So next slide, please. Yeah, we can see that there is a picture of the radar image. So we can find the picture of thunderstorm. uh, it is more realistic, and you can see that there are blue, green, yellow, and red color you can see here. So in the it is blue and green. These colors indicate the safe passage for an aircraft, and the red and yellow, these indicate the severe weather conditions. So it indicates that aircraft or the pilot should not follow these paths, and they should like take the paths with green and blue color. We can imagine how increasingly inclement weather can severely impact not just to ability the flight, but also to take off in the like in terminal. So with this radar image, we can find the best path to run the flight. Next slide, please. Yeah. The range of the severity we can understand with the help of this table. So here the intensity measurements are given with the colors. Blue and green colors, we can see these colors are showing the less intensity, and the intense and heavy intensity colors are red and yellow. So in this way we can understand the intensity rate. So in short, we can say that as higher the value of intensity, it is likely more likely for the severe weather occurrence and form of participation. So here the severity of weather is mentioned with the help of this table. So for an aircraft, it is safe to follow the paths of blue and green color according to the radar image. Next slide, please. Weather avoidance algorithm. Here we will discuss about the A* algorithm, which is informed search algorithm, and it is mainly and widely used informed search algorithm. It because it aims to find a path to the given goal node having the smallest cost, and also it uses the shortest path. It uses shortest path and the which have the smallest cost as well. So it does this by maintaining a tree of path originating from the start node and extending those paths of one edge at a time until its termination criterion is satisfied. So next slide, please. And besides being the shortest path and severe weather avoidance, the algorithm also lies within some criterion imposed by comfort level, pilot workload, etc. So in this algorithm, how does it work? So there is a formula, f of n equal to g of n and h of n. So where the f is basically the path, minimum path cost, g is basically uh, the actual cost of reaching the anchored goal, and it could be any node from starting node to the end node, and h is the estimated cost of the path from node n to the goal state. So the given formula is used to find the shortest and cheapest path. H is also known as the heuristic function, where node n is evaluated by combining values of the function g of n and h of n. The so next slide, please. Yeah, with the help of this example, we can understand the A star search algorithm and how does it work. So it takes the current state of the agent as input and produces the estimation of how close agent is from the goal. So with the example, we can see that here S is the root node and G is the goal node. Starting from the root node S and moving towards its successive nodes A and B to reach the goal node G. We calculate Fn value node of S, A and B using the evaluation equation. So in this way, we can find the shortest path and plus we can find these path with the minimal cost. So this is the A star search algorithm. Next slide, please, Vandana. Yeah. Well, the A search algorithm is a heuristic search algorithm and it is widely used, but it has some disadvantages and due to some disadvantages, and these disadvantages are like this algorithm is feasible when it is complete. It is feasible when it is when the branch factor is finite and has a fixed cost, and the performance of A star search is totally dependent on the accuracy of the heuristic algorithm. And major drawback one major drawback of one major disadvantage of this A search algorithm is its space complexity. So because what is a space complexity? It stores all generated nodes in memory. Thus, in practically travel routing system, it is generally outperformed by algorithms which can process by graph to attain better performance as well as memory bounded approaches. So here I'm done with my slides, and the next candidate is Monica. So you can continue.
Vandana, can you play the before slide? Yeah. My name is Monica Madrini. I would like to continue from thunder avoidance algorithm. Here, the figure depicts easy case wherein around selected lines that may be generated at each level are limited. If the start point and end point are not within the side of the root node, is the start point and the terminal node is the end point. This shows that thunderstorm lies in the accessible region. A thunderstorm lies in this path, then a moderate deviation is added to the distance. distance. Heuristic characteristic offers a higher estimate of the space quite straight line distance. If the number of nodes in the final path and quantity of memory allocated for node storage are properly chosen, the solution exists and it will be succeeded. Next slide, please. Here, in case 1, the first figure shows the radar image of the stationary thunderstorm that lies in the flight path. Inaccessible portion of the radar image can be determined as shown in the second figure. Here, in both the figures, 1 is the starting point and 2 is the ending point. Next slide, please. Here, the first figure illustrates the flight path in relation to the inaccessible locations, and the second figure shows the flight path in relation to the radar image. The smallest portion on the radar, the length is 10 units, and this program takes 11.4 seconds to secure option. Next slide, please. In case 2, the stationary thunderstorm that lies on the flight route is depicted in the second scenario. The smallest portion on the radar, the length is 8 units. Here, the flight path is depicted in the illustration as a diversion. The safest option takes the algorithm 11 seconds to compute the following. Next slide, please. Here in case 3, the thunderstorms are located in the initial flight route as shown in the radar image, which depicts the flight path led by the thunderstorm. The thunderstorm in the last 2 situations, both the airplane and the thunderstorm are traveling in the same speed, but a different algorithm computes a new direction for the airplane based on the current radar image. The aircraft then adjusts course as ordered by the thunderstorm avoidance algorithm. Next slide, please. Here, we have 2 cases. The one, and here I would like to tell about the picture first. The one enclosed by the red counter has intensity greater than 30 dB, and the one enclosed by the green has intensity greater than 20, and the one with red has intensity greater than 5. The dotted counter shows the intensity of the thunderstorm when the airplane is at the starting point. Counter position shows by the solid counters. In the meantime, a black line shows the path followed by the airplane. In case 4, a line of 3 thunderstorms is traveling at 40 miles per hour in positive x directions. In this scenario, the airplane is moving from point 1 to 2, which is a safe course. And in case 5, the line of thunderstorm can also be seen in the figure, which is followed by the airplane. In both scenarios, the plane safely avoids the collision. Next slide, please. Algorithm convergence and stability. The set of rules fails course lies in the location of severe thunderstorm and usually attempts to locate the answer within inside the ahead path. If the starting point is close to the destination, algorithm cannot trace the path. In the above cases, the recommended course comes very near the regions with excessive depth thunderstorms. Areas depth than 25 dB are set as inaccessible. Safer routes may be flight course. These set of rules work nicely if the given a small vicinity at the map. Instances set of rules path thunderstorm of turns within the site very last flight. Routes could make the set of rules computationally too expensive. Next slide, please. Coming to the summary and conclusion about this, in this paper, the bad weather avoidance algorithm was developed for the general aviation. This algorithm uses the principle of A-star search with some modifications to reduce time and space for the safe flight path. This algorithm is applied to 5 thunderstorm cases. The modification when applied to problems can endanger the optimality. The search tree has finite simulation. Results can be ensured by further tuning of algorithm. Thank you.